Good evening, everyone, or good morning, good afternoon, depending where you are in the world. So here in Luxembourg, we are like 8 p.m., so that's why I said good evening. Welcome to our final result announcement session for this Spark 2021 challenge. We are very happy to see you here. So sorry for the technical issues. We had some problems with communicating with ICIP for the platform, but hopefully everything is working fine now. I am first, sorry, I didn't introduce myself. I am Vincent Godillière, research associate at SNT, University of Luxembourg, and co-organizer of this challenge, along with LMO. So we are lucky to have with us Michel Pousset, CEO of LMO, that sponsored this challenge and that will present his company and the industrial context of the challenge in a minute. So this is the schedule of this session that will last around 45 minutes. So first, I will ask Michel Pousset to speak about space situational awareness. Hello, Michel. Good to see you here. So you are muted. Just 1 second. As soon as I finish, you will be unmuted. Sorry, Michel. So you will first present the industrial context, as I said, as well as the winners of the challenge. Then we will have 2 presentations from the 2 winners, one for the winner by the winner of task 1 classification, and one by the winner of task 2 detection. And then I will conclude with a summary of this first edition of the Spark Challenge and a few words about what next. So again, thank you, everyone. Michel, please, this is your turn.
Okay, yes, now I can unmute myself and share. Perfect. Thank you very much, Vincent. And thank you very much, SNT, for preparing the challenge, hosting this event at ICIP. So my name is Michel Pousset. I'm the CEO of LMO, and I'll be sharing a bit the context of what we are doing with the University of Luxembourg and the SNT department, and more in detail, the computer vision group at the SNT department at the University of Luxembourg, and why we implemented this challenge so that we could reach out to the overall computer vision community and start having others look at the challenges we face day to day in our developments. So let me see if I can share my screen. Hope everyone can see this. You don't, Vincent, just let me know. But anyway, as I said, we've been working with the University of Luxembourg on space situational awareness technologies or developments in the last few years. We set up this challenge, so I thought I'd bring you through which context the challenge will be used, or the technology behind it are being applied to. So I know this is not a space community. There might be some space enthusiasts, some people working from the space industry. However, there's a lot of things going on above our heads in space. We're launching more and more satellites into space to support us with GPS, with communications, with looking at Earth observations for climate change, and it is getting busy up there. And the more and more it gets busy, the more threats there are of collisions, of satellites breaking down and hitting into others. Together with this, there's a more opportunity As we use space more, as we explore further, we're looking at a new in-space economy where we assemble objects in space, we can repair objects in space, and we can actually refuel and create new ecosystems further and further away from Earth. However, we do all of this sitting on ground. The view is beautiful in some places, but this really limits the possibilities and capabilities of what we can do in space. When we drive our car, we don't say, have someone remotely controlling it. We sit in ourselves. We now have developed autonomy on cars to let them drive. This is very similar to what we're looking at today. So what we're looking at LMO is to change our point of view from having this, steering things from afar, to actually leveling ourselves up and operating in space. So move the point of view so we can enable autonomy for in-space operations. Now, 99% of operations in space are run by people within ground locations, looking at what's happening, acquiring information in space, transferring that on ground. They plan, they check, they resend up information so that then a satellite can work or operate in space and make decisions based on what happened on ground. The time this happens is very long. There's lag, and with things moving 1,000 miles an hour in space, it limits the amount of operations a satellite can do. So satellites today are quite lonely. They operate in orbits on their own. They don't cooperate much with their objects, hence why, like I said, other objects are threats. What we are trying to do is to bring autonomy within the spacecraft. So we remove the human interaction, remove any decision process on ground, and we bring that decision process in space, directly on the spacecraft. So a spacecraft can have sensors on board to have a situational awareness or space situational awareness of what's happening around it. It can actually look, then it can check, it can plan, and then with the command, it can act in space so that they can collaborate with other bodies by approaching them or move away. In order to do that, we need to do I'm not a computer vision expert, but what is standardly done in computer vision, that's detection and classification. What are we seeing around us? Object feature recognition, as we get close, how is our objects around us split? So where are solar panels, where are fueling ports, where are docking arrangements, so that we understand how to behave around them. And last but not least, the pose estimation. So 6 degrees of freedom, how are these objects translating or rotating with respect to us so that we can approach them and actually dock to them. If we can crack this nut, we'll be able to solve many problems in space. However, one big thing we have is we've developed a lot of algorithms on ground for self-driving cars, other applications, and we've got big halls of computers on ground where we can run algorithms. But in space, things are a bit more limited. We have quite antiquated electronics, which we are developing, or the community is developing. We don't use much AI or machine learning algorithms in space, and we have certain limited sensors. So at LMO, we are collecting all that information, collecting all those different technologies to actually make a unit which can create autonomous decisions in space. So you grab space sensors, which have already been qualified. These are quite limited in capability, but we enhance them with the computer vision algorithms, which we try to run on space-grade electronics, which I said are limited in processing capabilities. A bit similar to how the sensors on board of modern iPhones or other smartphones are limited, the computer vision algorithms enhance their capability and make them do more. By doing this, we can start looking at inspecting things in space. So actually do autonomous inspection. Are satellites broken? Is the satellite a threat? Is it a piece of debris coming our way? We can start looking at what's called servicing in space. So if I know how an object, what it has, or where the fueling port is, or the attachment port is, and I understand how it's moving, I can approach it, use robotic arms or other elements to dock with it. And last but not least, when we go explore beyond on other planetary surfaces, or on the moon, on Mars, we can use computer vision to autonomously navigate our rovers to understand the terrain in front of us and actually operate in the conditions. So we as LMO, we're a Luxembourg-based company. We are supported and work with our local research institute and research funding groups. So the Fonds National de Recherche has been funding a lot of our developments. We work with the Space Agency in Luxembourg to bring forward our developments. And last but not least, we work together with the brilliant computer vision group from Jamila at the SNT, with Vincent, Mohamed, Albert, Miguel, and others who've been supporting us along the way. And we're a small team still in Luxembourg of 5. We're hiring, we're opening up to what is called the guidance and navigation and control engineer. Anyone from the space industry who's interested, we have an open position. So why did we do the Spark Challenge? Well, by working with S&T and others, we know there's a lot of advances in computer vision on ground, which is really mind-boggling what is happening. There's been a lot of advances in space electronics. And last but not least, finally, there's a bit of access to space representative data sets. We are generating our own. Other companies are, the European Space Agency. So it's now time, we feel, to really bring the space and computer vision communities expertise so we can identify the best techniques to apply on the limited electronics architectures we have, but reach the maximum potential so that we can meet the autonomy in space. So if I go back to our goal of providing autonomy, where we said we're going to do detection and classification, feature recognition, and pose estimation, we really focus on that first building block, which is detection and classification. These were the two main challenges we put out in the Spark Challenge, for which we had multiple companies, universities, people engage. We were really happy with the results and everything. And it's actually, we hope that this will bring the whole community forward in meeting our objectives. So I'd like to thank everyone for that. And again, I'd like to thank S&T. So based on this, I'd like to head to those people who put a lot of time and effort into these challenges and go forward to announce our winners. So we had two tasks. The first one was focused on classification, where again, we have multiple entries coming to the challenge. And based on this, we've given a second and a first place prize. So in second place, I'd like to congratulate Sun-Hao Chu from the Shanghai Jiao Tong University for his contribution to the classification challenge. He'll be awarded a prize which we're funding, and I hope he uses that well. So congratulations, Sun-Hao Chu. Then in first place, congratulations to Michael Schleiss from the Fraunhofer Institute. He was our number one, and he was awarded €200 for Spark Classification Challenge. So well done to that. And then we will move over to the bigger challenge, the detection challenge, which was task 2, where again we had numerous entries from institute, universities, and others. So in second place here we have Nuhar Al-Dahul from the Yo Vivo Corporation, who came second in the Spark Detection Challenge. So congratulations for that. Thank you very much. Well done. And then we go to the grand prize winner, the person who came first in our Spark Detection Challenge. And that is again Sun-Hao Chu. So congratulations for your second place in the classification, but also your first place in the Spark Detection Challenge. For you, the grand prize of €500, sponsored by the consortium. So well done. And I already see Mohammed, one of our researchers, clapping. So again, congratulations to Sun-Hao Chu, to all the rest who have contributed and who were awarded awards in this challenge. We hope that this has brought forward the interest in space situational awareness and the developments which are being done for space. So based on this, I believe the winners of each challenge are going to do a small presentation of their work and provide us some insights. So I'm really looking forward to that. I think it now goes over to Vincent again. You there, Vincent, or just wait a second?
Yeah, thanks, Mohammed. Sorry for this technical issue. So I have the sound now. I just need to connect to share my screen. Mohammed, can you please? I think you need to give me the right to do it. Okay, thanks, Mohammed. Okay. So now, thanks a lot, Michel, for your presentation, for your support also in this challenge, and for having announced the winners. So yeah, again, I would like to thank really all of you, not only the winners, but really all of you that did a great job. So now it's time for the two winners to do a presentation. Unfortunately, I received a notification from Michael Schleiss, and he won't be with us. He's not with us tonight, so we cannot see his presentation. So we will jump directly to the winner of the second task, Sunhao Chu. Sorry for the presentation if it's incorrect. Somehow, don't hesitate to join us if you can. So maybe Mohammed, you will need to unmute him and enable him also to share his screen if he is with us. Somehow, are you here? We cannot hear you now.
Can you hear me?
Ah, perfect, perfect.
Hello everyone. My name is Sunhao Chu, a PhD student at Shanghai Jiao Tong University. I am honored to give a presentation about my method to the Spark Challenge. Since the first artificial satellite, Sputnik, was launched in 1957, the amount of man-made objects sent into space has grown exponentially. Acquire information and knowledge about objects orbiting around the Earth, which known as space situation awareness, has become an important research topic. The purpose of this challenge is to apply the state-of-the-art technology in computer vision community to spacecraft perception tasks to achieve classification and localization. Because of the resolution of the depth image in Spark dataset is much lower than the RGB image, I decided to use only RGB image in my method. Object detection algorithm using convolutional neural network can be divided into one-stage method and a two-stage method. To the best of my knowledge, one-stage method represented by Euler series has been better developed because of its higher precision and speed. As of the beginning of the challenge, Euler V5, proposed by Ultralytics, is the most advanced object detection algorithm. Euler V5 is available in 4 models, namely S, M, L, and X. Each one of them offering different detection accuracy and performance as shown in this figure. we can use depth parameters and width parameters to get 4 variants of the model. Among them, Euro V5S is the simplest version with the smallest model parameters and the fastest detection speed. Euro V5 divides the network into 3 parts. One is the backbone network part for feature extraction. Neck part for feature enhancement, and the head part for prediction. Let me introduce the pipeline of the algorithm. First of all, in order to speed up training and transfer learning, the image is resized to 640 times 640, and then go through a series of image augmentation methods, including mosaic, cut mix, cut out, mix up, and then the image is fed into the neural network. Focus module is designed to concentrate the information of H and W dimension on the channel C dimension for flops reduction and speed increase. The input will be transformed like this. Batch size, channels, height, width to batch size, 1/4 of channels. 4 times channels, half height, half width. Then I will introduce the CSP module. CSP module first divides the feature mapping of the basic layer into 2 parts, then combines them through the cross-stage hierarchical structure, which reduces the amount of the calculation and ensures accuracy. In the last part of the backbone network, using the SPP network, this module can further expand the receptive field and helps to separate contextual features. Then I will introduce the next part of the Euro V5 network. The feature enhancement part is used to further improve the feature extraction ability. It uses the idea of path aggregation network, PAN, to design the structure of FPN plus PAN. First, it uses the FPN structure to convey strong semantic features from top to bottom, and then uses the feature pyramid structure constructed by the PAN module to convey strong positioning features from bottom to top. Through this method, it is used to fuse features between different layers. For the head part inherits the head structure of Euro V3, which has 3 branches. The prediction information includes object coordinates, category, and confidence. The main improvement is to use complete intersection over union loss, CIOU, as the bounding box region loss. For my first result submission, I train and evaluate the Spark dataset on the 4 different Euro V5 variants and set the iteration number of model training to 40 epochs. The training and validation loss are shown in this figure. This figure shows the comparison of COCO metrics of 4 models of Euro V5 on Spark dataset. In order to further improve the detection accuracy, I use Euro V5X model and set the number of epochs to the last submission to 200. The training and the validation loss and the detection performance of each category is shown in this figure and this table. That's all. Thanks for listening.
Thanks a lot, somehow. Thank you very much for your presentation. It was very interesting. Also, thanks a lot for your work. We'll see later that you achieve a very high performance on the testing set. So now I would like to allow people to ask you questions, maybe. So can you please raise your hand, and Mohammed will give you access to the sound.
We just have one question related that you only used from one participant. You only used the RGB images.
Yes, I only use the RGB image.
Okay. Thank you.
Yes, thanks, Ishraf, for your question on the chat. Other people, if you want, you can ask a question through the chat, or you can just ask for the microphone. Okay, so if there is no more question, thanks a lot again, Senhao. Thanks a lot for your participation, and we hope to see you again in the future, and we will contact you for sure for the award. So yeah, Michel Pousset is applauding you, and so do I. So yeah, thanks again. So Mohammed, please, can you allow me to share my screen again? Yeah, okay. Thanks, Mohammed. Okay, so now I will do a brief summary of this first edition of the Spark Challenge, and then say a few words about the perspectives. So for now, I would like maybe to introduce someone that, so it's called Mohammed. He's a PhD student in our research group, CVI2 at SNT University of Luxembourg. And he did most of the job regarding the Spark simulator and the generating the data. And he's also multitasking because he's our technical engineer tonight for this session. So Mohammed, thank you a lot for all your work. And can you please just present in a few words the data?
Yeah. Can you hear me now?
Yes.
Okay. Thank you, Vincent, and thank you for your work with the Spark Challenge and the Spark dataset. So overall, the main problem that we face with space situational awareness, or with any other problem in computer vision, especially with the deep learning, now, that what we need is data, and a lot of it in different modularity and in different distribution. And as it's hard actually to start just collecting data from space because it's expensive and we are not in space. What we now currently rely on is to start having a simulator, and currently we build our own simulator based on Unity 3D game engine with high resolution Earth model, different spacecraft, different camera modularities, And the idea is also to sample from different axes of distribution, like different illumination condition, background, either space or earth, different distances from the camera to the target, and different optical noise sensor. And the idea is also to add more realistic condition for this dataset. We add more ISO noise, like the digital sensor, real digital sensor noise, different Gaussian distribution noise, some kind of trying to make the synthetic data more realistic, to have different, like similar cases to what you can face if you're doing a digital camera or or collecting image from a spacecraft, especially with a small camera sensor, because you have constraint on the power and the digital. So the Spark dataset is considered the most diverse dataset in the problem of space situational awareness until now, spanning with different modularity from, as some of them you already shared on the dataset. You can have Vincent, please, next slide. Yeah, so we have 150,000 high resolution RGB, and the same with depth image, but with different resolution, segmentation mask, which will be shared after the challenge, bounding box annotation for 10 different satellites, and 12,500 satellite, and 5 different debris objects with 5,000 each of them. And we can see here that the distribution of the illumination and the distances is quite diverse. So we can have different satellites in close range, in far range, images with high luminance level and low luminance level. Next slide, please. So I think Vincent now.
Yeah.
Continue.
Thanks a lot, Mohammed.
Thanks.
So maybe why ICIP for this first edition of the Spark Challenge? Simply because this is the largest image processing conference, and in this first edition we proposed 2 tasks that are really related to image level. Again, the first task was referring to spacecraft image classification, and second task, spacecraft detection. So we encountered quite a success with this challenge, with more than 40 people until a certain date, more now, but it was too late to accept them, but more than 40 registration, and finally 17 submissions from 5 participants. So when I say submission, I mean results plus reports describing the methods. A brief summary of the data used in this challenge. So not all the data available through the Spark simulator was proposed. So only a subset of them. So RGB images with depth images to allow participants to investigate the use of multimodality to tackle these tasks. And the green truth labels were constituted of classes for the classification challenge and bounding boxes for the detection. So we release this data into 3 batches, a first batch for training, a second batch for validation, both of them with green truth, and the last batch for testing without the green truth, of course. A few words about the evaluation metrics. So for the first task, classification task, we proposed 11 classes. So 10 classes per satellite, so 1 satellite per class, and 1 class called debris, in which we had 5 different debris models. So since there is no straightforward approach for classification evaluation, in fact, depends what good means for good classifier. What does it mean? And in fact, good refers to the actual real world problem that we want to solve. So in binary classifications, the classical metrics are precision, that measures the proportion of predicted positives that is truly positive. So if we put the emphasis on this metric, it means that we don't want, or we want to minimize the number of false alarms. Then the opposite, let's say, metric called the recall measures the proportion of actual positives that is correctly classified. So here, if you put the emphasis on the recall instead of the precision, it means that you want to minimize the number of omissions. And then to, let's say, combine these two metrics into just one scalar metric, well, we often use the F-beta score. That is a way to combine precision and recall using a scalar factor beta. So depending on this value, we give more importance either to the precision or to the recall. So if we use a beta greater than 1, it means that we give more importance to the recall. And if we put a beta lower than 1, it means that we give more importance to the precision. And beta equal to 1 means so an harmonic mean between precision and recall, so the same importance on both. So here for the multi-class, we had our problem was multi-class evaluation problem, not only a binary classification problem. So in multi-class classification, we can either use the same criteria for all classes and then do an arithmetic average, for instance, of the recalls or the precision or the F-beta scores. If the data set is unbalanced, we can weight this average, or if we want to give more importance to one subset of the data set. And if we have no specific criteria to evaluate, we can just compute the overall accuracy, that is simply the proportion of samples that are correctly classified. Now, in this task provided by LMO, we had some insights to evaluate the submissions. So the problem was, if we classify a satellite as a wrong satellite, this is a mistake, but this is not of high importance. We call it an inaccuracy. Now, if we classify a satellite as a debris, the level of seriousness is higher. And classifying a satellite as a debris can be referred as a false alarm in our case. And now, the worst case is classifying a debris as a satellite. That is an omission, and we want to put more importance on this to discriminate the submissions. So from these insights, we derived a problem-oriented metric that is the following. So we measure the F2 score for the debris, again, because we gave twice more importance to the recall than to the debris, than to the precision, sorry, for the debris class. And we use the balance metric to measure the performance over all the satellites. So finally, the performance was the F2 score on the debris class plus an overall accuracy on all the 10 satellite classes. Now for the detection, so the criteria most often used for evaluating submission in this kind of task is the intersection over union. So we measure the overlap between the ground truth bounding box and the predicted bounding box. And we measure the overlap, the intersection, the area of the intersection, and we divide it by the area of the union of the two bounding boxes. And we also wanted to evaluate the classification accuracy in this task. So we didn't ask the participant just to predict the correct position and size for the bounding box, but also the correct label. So finally, we relied on a metric inspired by the one used in the Cocotte challenge. That was basically a percentage of prediction with correct label, and an intersection over union score that is above a certain threshold, and we average it over different thresholds. Now, here is the split we used for the awards. So 300 euros, again, thanks LMO for this, 300 euros on the task one, 200 for the first one and 100 for the second one, and 700 euros on the task two, the most difficult one. So 500 euros for the first one and 200 euros for the second one. Here is the overall results for the classification task. So again, Michael Schleiss from Fraunhofer that achieved a high score of 1.9973. So out of 2, so almost a perfect score. Also for Senao Chu, again, sorry for the pronunciation. And Shubham Chaudhary also that achieved an excellent score, Nuhar and Ishraf. So thank you very much for your participations. Now for detection, so somehow achieved an excellent score again, 0.9, more than 0.9, and this is quite difficult task. And yeah, Noir and Michael also did a great job. So just a few words about a paper we published in the proceedings of this grand challenge at ICIP. So it's an overall analysis of your submissions. So in them, we don't release the name of the winners, but we perform an overall analysis of all the submissions together. So I invite you to take a look to this paper, so called Spark Simulator Dataset Competition Design and Analysis. I don't have time now to present the results in detail because we are already late, but feel free to take a look to this paper if you want to know more about the participations. So what next? Of course, we are going to contact the winners to grant them the awards provided by LMO. And of course, so this was the first edition of the Spark Challenge. We noticed that it raised a certain level of interest from the community. So we would like to go for a second edition in 2022. Of course, the main topic of it will stay the space situational awareness, but we will try to provide additional features for this second edition. So we will introduce a trajectory estimation task. So we will add a time component for the challenge. We will introduce also not only simulated data, but also laboratory data. We will also propose a baseline method for the participant to compare with, and probably other surprises also. So thanks a lot for your attention. I see that you were a lot in this session, so thank you very much. And we hope to see you next year for the second edition. And before forgetting, Federica from ICIP asked me to tell you to go to the Zoom link now provided by ICIP to join the, let's say, official ICIP Grand Challenge session. So thank you very much again, all of you. Bye.
Also, feel free to join the Gather platform to see the posters and interact with the participants and the authors. Thank you, everyone.